Welcome back to lecture 6, and let's have a look at another problem that is related with the transient systems of, like for example, if we are talking about in cooling or heating. So this particular problem is related with transient cooling system. Okay, so the aluminium cylinder described below has a specific heat capacity of 903 joule per kg per Kelvin, and it has a density of 2702 kilograms per meter cube. And at the time zero, the temperature of the aluminium cylinder is 300 degrees centigrade. Okay, and then you place that cylinder in a temperature, for example, in water, and the water has a temperature of 25 degrees centigrade. Okay, so way below the temperature of the aluminium cylinder. So the cylinder is going to lose heat via convection heat transfer, and you know the value of the heat transfer coefficient for convection. So now the question is, how long will it take for the temperature of the cylinder to drop to 75 degrees centigrade? Okay, and we know the dimensions of aluminium cylinder itself. We know what is the size of it, the length of it, we know the diameter, so it means that we can easily calculate the surface area of the cylinder. We know the thermal conductivity of aluminium as well, so we can look at how much time it will take to drop to 75 degrees centigrade. So if you look at this problem, this kind of analysis can be used in our practical life as well. For example, just looking at it, that if you have some food or some metal or whatever kind of material, and you want to just know how quickly it will take for that material to cool down before you can touch it, or you can use it, so you can use this kind of analysis. So this is very much relevant to our daily life as well. So before we go and look into the solution of this problem, let me introduce you another new concept that is called characteristic length, because we are going to use this concept in this solution. So a characteristic length is a key parameter that we very often use in heat transfer problems, and it is used to simplify complex systems. And by using characteristic length, we assume that the system or the object has a uniform distribution of temperature. And by making this assumption, we can actually neglect any temperature difference between different parts of the object. So for example, if we have this cylinder, we can assume that this whole cylinder has a uniform distribution of temperature, and as such we can calculate its characteristic length. So this characteristic length can be calculated by taking the ratio of the volume to the total convective surface area of the object. Okay, so for example, if we are talking about a sphere, so the characteristic length of the sphere would be its volume, that is 4 by 3 pi r cube, divided by the surface area, that is 4 pi r square. And if you obviously simplify it, we can write the characteristic length as d over 6. Similarly, for a slab, we can calculate, if a slab is heated on both sides, the characteristic length of the slab would be half the thickness of the slab. And for a circular tube like a cylinder, as you can see here, we can also calculate its surface characteristic length by taking the ratio of its volume, so volume of the cylinder, divided by the total surface area. So in this case, the total surface area would be the surface area on this side, that is the cross-sectional area here, the cross-sectional area here, and the surface area. So it will be A1 plus A2 plus A3. Okay. So we know that when we did the transient cooling and heating system analysis, we came up with this equation here that is a long equation, and we don't expect you to remember. For example, this kind of equations will be provided to you in exam. So when he has already provided you a list of equations, so that similar style equation list should be kind of provided to you in the exam as well. Okay. So if you look at now these equations, what you have on the left hand side, you have the temperature fraction that looks at the temperature difference between, for example, the environment, of the surrounding, minus an arbitrary temperature or a transient temperature, and it has a ratio with a temperature difference, again the surrounding temperature minus the starting temperature of the system. Okay, and then on the right hand side we have a long equation, but if we look at the last term, so you have exponential of minus t over tau, and t is the time, the arbitrary time, just like the temperature here. So it means that the temperature value here depends on the value of the time itself. And we have the other characteristic time that is called tau, and tau is a constant. It means that once you decided to choose your system, like you know what kind of fluid you have, what kind of equipment you have, you actually fix the value of tau. Okay, so if you change your system in terms of material or in terms of the fluid, then you will have another tau. Okay, so for a fixed system, your tau is fixed. So it depends on Cp, that is the heat capacity of the system, m, that is the mass of the system, U, that is the overall heat transfer coefficient, and A, that is the surface area of the system. So now if we look at this equation, we just need to calculate tau from the given data, and once you know tau, you can actually feed back to this long equation, and then we can look at different temperatures and feed into that, and then we can calculate the value of time. Okay, so this is fairly easy question, but it's important to understand how to use this formulation. So we start with our equation of tau, that is equal to mCp over UA, and we can break down this m into rho v by the definition of density, and we can further break down area volume into area times ls, and ls is the characteristic length of the system, and we can see that the area here will cancel out in the area that is in the volume. Okay, so we only have ls, and now we have u at the in the denominator. We can calculate ls. So ls is the characteristic length, and as I explained, that it is the ratio of the volume over total surface area. And so for a cylindrical tube, we have v over as, and we can write the volume as pi r square L over 2 pi r square, because we have two cross-sectional areas, so one on the left side and one on the right side, so that's why we have two here. And then we have the surface area of the cylinder, that is 2 pi rl. Okay, so if you put the value of different parameters that we have, so we know diameter of the cylinder is 5 centimeters, so it would be r would be 2.5 centimeter, and L is given as 5 centimeter. Okay, so if you put the values of R and L in this equation, the LS comes to be 0.83 centimeter, and if we write it in SI unit in meter, so it will be 0.0083 meter. Okay, so now we know the value of LS. We can feed the values of different parameters in tau equation, so we know the density of the system is given to us. We know the value of ls, we know the value of Cp, and we know the value of U, that is the overall heat transfer coefficient, that is given to us as well, and we get tau is equal to 203 seconds. Okay, so we know our characteristic time. Now we can further solve it for the time. So from the previous equation, we can again plug the values of different temperatures. So the initial temperature of the cylinder 25 degrees centigrade, the target temperature of 75 degrees centigrade, and 25 is the temperature of the surrounding, 75 is our target temperature, and then we have 300, that is the initial temperature of the cylinder. So we can rearrange this equation, we can take log on both sides, and we can write in form of T, and T would be equal to 203, that is the value of tau, times ln of this temperature fraction, and if you solve it, we get 346 seconds, that is approximately 6 minutes. So what it shows us that if we have a cylinder or any metal object that is at 300 degrees centigrade, and if we put it in a surrounding of temperature 25 degrees centigrade, and it will take 6 minutes roughly to reach a temperature of 75 degrees centigrade. Okay, so by using this transient analysis, we can calculate how long it takes for the temperature to drop from an initial value to a targeted value.